Many a times IoT is described by many as a rebranding of traditional embedded systems. Though, it is true that IoT devices are actually embedded devices, however, working in a connected paraphernalia, they cast many more capabilities as a system than what was conventionally achievable. To start with, in conventional settings, embedded devices perform specified or programmed functions, generally in an isolated manner. Like, for example, a simple TV remote itself is an embedded device, a simple digital watch is an embedded device, which perform what they are programmed to do, over and over again. Commonly, in the embedded systems, different devices either operate in isolation or in combination wherein, interconnectivity between them can either be like a bus of communication, or they can be arranged in point-to-point topology according to the system design requirements. This produces a bit of rigid designs, wherein specific devices are designed to work in specified settings. Though with the passage of time, technology has grown tremendously. The three key areas that are worth mentioning in our current discussion include Moore's Law, improvements in connectivity infrastructure over the years, and the evolution of data science and the artificial intelligence. All these areas have contributed into making IoT stand out from old and gold system designs. Data science itself is a separate vast field, and beyond the scope of our discussion here. But it suffices to know that studying data through scientific methods is data science, that produces results in a way that have never been imagined. Moore's Law presents an observation that the number of transistors in an integrated circuit or an IC doubles about every 2 years. Although this is an approximation, but more and more computing power is incrementally being provided on a same-sized chip, with every passing year. Over the decades, it still largely holds true. Because of increasing, higher level of integration, many of modern day's microcontrollers are becoming more and more computationally powerful than the excellent processors were from just a decade ago. Not only the devices are becoming more and more computationally powerful, but their prices are also reducing due to higher production volumes and improved production processes. The second enabling factor of IoT is the improving capacity, reliability, and increasing data rates of communication infrastructure, thereby allowing near real-time connectivity between devices and back-end infrastructure with huge data handling and computational capacities. Therefore, when compared with the traditional embedded systems, IoT is actually a concept of virtually connecting the embedded devices together over a connectivity backbone of Internet, thereby allowing sharing of data with each other in addition to consuming data from other online data sources, thus utilizing the full power of Internet. In this context, a relatively newer term of edge devices has emerged that refers to physical devices with good enough computing resources. In parallel, you might have come across the term edge computing, which generally refers to fully utilizing the computational power of edge devices for reducing communication overheads and to produce real-time results for users. For example, implementing computer vision and object detection in the edge devices instead of at some server running in a public cloud. For instance, an IoT-enabled washing machine can access electricity prices and water availability in the local area, and use the data to wash clothes with minimum costs incurred. We can have numerous examples of IoT devices ranging from home automation and wearables, to professional aerial and ground-based security robots. Even wearable medical devices can track a patient's health indicators and automatically call up for help in case any emergency situation arises, or even track personal data to help doctors in diagnosis. On transportation and logistics side, IoT is helping in inventory management, items tracking, and cost reduction. In short, every field ranging from personal domain to national defense is highly affectable by the Internet of Things. According to Statista, there are currently more than 13 billion IoT devices, and the number is expected to be more than doubled before the year 2030. With this description of IoT, we can draw on some characteristic features of it that make IoT stand out as a separately emerging field, and as a combination of different disciplines mixed with the traditional embedded systems. The first differentiating element of IoT is gathering and consuming large amounts of data at scale to better understand the world around us, and to utilize the data in producing value. In this case, online services are available to be used. For example, weather information can be used to initiate certain actions by IoT-enabled devices, like for example, if the historical data implies that certain kind of weather conditions within a localized area cause certain types of diseases, then the IoT-enabled health devices can detect weather conditions to initiate remedial actions in advance. Secondly, people don't lie with their own devices. So, users' activities are of high importance in decision-making by manufacturers. For example, if certain percentage of users within an area are using steps counting apps on their smartwatches, then it can be implied that that area's residents are more conscious about their health and physical activities. Therefore, this information can very well be utilized to introducing better devices that suit majority's preferences, and special events can be organized according to majority's taste. This kind of data gathering and consumption specifically makes IoT fruitful for both consumers and producers, as products are tailored to be made better according to end users' preferences. 1 zettabyte equals a trillion gigabytes. So, the number is huge beyond any doubts. According to Statista survey from year 2010 till 2020, the amount of data or information created, captured, copied and consumed worldwide grew from just 2 zettabytes in year 2010 to more than 64 zettabytes in 2020, with expectations of 181 zettabytes in 2025 alone. Where does this huge data come from? Obviously, very small portion of data is human-generated in the form of text, speech or video content. The greater portion is from devices like sensors and other information sources. Though, this huge data has played key role in the uprising and maturity of artificial intelligence and machine learning, which when combined with IoT can produce results beyond imagination. The second aspect that makes IoT different from previous technologies banks on the available computational power both at the edge devices and at the backing services in public or private cloud. For example, a smart robot can take a stream of images to detect threats, wherein the backing services with a huge compute power can train on multiple sources of data and disseminate learnt results to the edge devices, so that near real-time results can be achieved. In combination, they can produce a larger impact as far as the system composition is concerned. Like, for instance, a system of aerial robots can inspect a gas or oil pipeline for detecting flaws in humanly hard-to-reach areas, and can raise alarms through systematic processing, while collaborating with other robots within the area of coverage, and ensuring timely recharge of batteries without affecting system's performance or downtime. Wherein, the devices are made smart in themselves that can capture information and data, and can draw individual decisions. Devices connected through backing services in the whole system can interact and share information with each other, so as to create a whole system that customizes users' world in accordance with users' preferences. Thus, from the enabling nature of IoT, we can draw few elements that describe the kinds of problems that Internet of Things can solve. In a sense, such things highlight that why we should at the very least care about IoT devices. The first thing that IoT cares about is creating systems that are targeted towards individual user preferences and environment, as the designs are data-driven themselves, and also use data during functioning. Thus, user-oriented designs are targeting users' problems effectively while creating value. For example, a user can automate his or her home or living space according to personal taste, and even change the arrangement of environment for certain occasions with just a single command by speaking with assistant applications, or by pressing a button. Though, IoT-powered systems cost more in terms of money when compared with traditional embedded systems, but they offer greater value in terms of users' preferences and ease of making decisions. They additionally can save material costs over time. For example, saving electricity by switching off unneeded devices, and by planning cleaning tasks when the electricity is costing minimum. Lastly, IoT allows flexibility in system designs, gracefully adapting to working environment, wherein the complete system design can be broken down into smaller, well-designed parts, each connected through the internet and functioning to give illusion of a whole system in combination. This approach enhances collaborative designs, and well-designed systems can allow remote upgrades, thus allowing quicker times to market while still allowing fixing issues and introducing newer features without physically getting back the products from end users. Another very important element is graceful degradation, wherein, whenever physical or other flaws are discovered in any system, the system can still operate but not at a maximum limit. For example, if an IoT-enabled weightlifter can lift 100 tons of load, and after certain hours of operation its sensors detect some cracks in its main architectural parts, then without returning to maintenance site, the information can be remotely communicated to its manufacturer, which can study the problem and update its upcoming designs, and remotely authorize the lifter to lift lesser load while staying safe for operation, which ultimately improves functioning and better designs. By no means, examples quoted in this session comprise a whole list or cover all the aspects. From distributed manufacturing robots to remotely done medical procedures, IoT is enabling modern innovative technologies. By and large, IoT can be treated as a concept, not as a hardline field of study.